this invitation. And so, sorry, I cannot see, but can you see normally? Maybe I don't understand if it's a local problem for me.
We see normally. We see Jan's first page.
Great.
Okay. So
I think you cannot see my
okay.
face.
So now it's time for Jan Nechita. I'm very happy he accepted our invitation, and Jan works in the Laboratoire de Physique Théorique in Toulouse. And today he will speak us about enumerating meanders, three perspective. Please, Jan.
Thank you, Rafaela, and thanks to all the organizers for the invitation to attend and to speak at this this very nice conference. I'm very honored to be a part of this. So today I decided to tell you a story about meanders. So these are combinatorial objects which are quite famous in combinatorics, and they have received a lot of attention because as you will see, it's quite hard to get a grasp on counting these objects. And more recently, there have been many connections between these meanders and different areas of mathematics, and I will try to give you a flavor of these connections. Unfortunately, I think my talk is a bit off topic, so I apologize for this, but I still hope that you will get something out of this. I try to be very I try to present some of these new results I have obtained with my collaborator Motohisa Fukuda from Yamagata University in Japan. But I will spend quite some time on the history and on the setup. So I try to be quite basic. So please feel free to interrupt me if things are not clear or you would like me to give more details. So here is the plan of the talk. I will start by presenting the problem. So by explaining what these meanders, these combinatorial objects are, and then the following three topics I would like to touch upon are the first to deal with the connection between these meanders and free probability theory and non-commutative probability in general. And in the last section, I will present some random matrix models, which will maybe emphasize the connection to this third topic that I mentioned, which is quantum information theory. So basically, in the first part, it will be mostly combinatorics, then some non-commutative probability, and finally some random matrix theory and quantum information theory. Okay, so let's go. So what are meanders? So basically, a meander is what this picture shows here. So we have this horizontal straight line, and we have a closed curve which will intersect this, which is not self-intersecting, and it will intersect this horizontal line in two endpoints, so in an even number of points. So this is a meander of order n. So the meander is the thing in red, is the curve in red. Well, we would like to relax this definition to allow for several connected components. So with several such closed curves, and it will be interesting in enumerating these configurations. So the main goal is to see how many meanders are on a given number of even points. Okay, so the difference between a meander and this more general object, which is a mandric system, is that a meander is basically a mandric system like this, but where we have one connected component. Here you see you have two connected components. You have this one in the middle and the sausage-shaped thing on the outside. Okay, so basically what's happening is that the main problem in combinatorics, which is a big open problem, and there are many things known, but still the problem of enumerating these objects and counting how many there are is still wide open, is about these objects, about the meanders. So how many such loops on two endpoints are there? Okay, and let me already point out. So I will give a list of references in the end, but there is this very nice paper by Francesco and collaborators, which is kind of a review paper, and they gather many of the known results and approaches about this problem here. Okay, so with this picture in mind, let us move to a more precise definition. So basically, the idea is that a meander is built out of two parts. So I will look at the top part over this horizontal line and the bottom part, and these objects are of the same type. They are called arches, so sometimes they are called arches, but mathematically they correspond to non-crossing pairings. You see, so I have 2 endpoints here. I have 2, 4, 6, 8, 10 points, and you see I have pairings between these points. And what's important is that since I want my curves to be non-intersecting, I want my pairings on these 2 endpoints to be non-crossing, meaning that whenever I have 4 points, or whenever I have two pairs, so AIBI and AJBJ, I want them to be non-intersecting. So I don't want a configuration like this where here the pair AIBI intersects the pair AJBJ. You see, I don't allow for these kind of intersections in pairings. So basically, a meandric system is an object built out of two such non-crossing pairings, right? One on the top and one on the bottom. And let me remind you or tell you about this very important bijection between non-crossing pairings on 2 endpoints and non-crossing partitions on endpoints. So there is a one-to-one correspondence between these types of combinatorial objects, which I depict here. So on the left, you have the non-crossing pairing, which was shown above, and the way to build a non-crossing partition out of this, it's called unfattening. So basically, what you do is between consecutive pairs of points, you build the largest partition, the largest block you can squeeze in between. So here you see I can put this block of length 3 here. Here I can put just a singleton, and here just again a singleton, and I get this non-crossing partition here. So again, it is non-crossing, so you don't allow for the blocks to cross. But now it is more general. It is a general partition. So here I can have a block of length 3. So not necessarily pairings, right? So this is a one-to-one bijection, a one-to-one map, and both these sets, so non-crossing pairings on 2 endpoints and non-crossing partitions, these are counted by the famous Catalan numbers. And here is the mathematical definition I will use for Mandric systems. So these are just pairs of 2 either non-crossing pairings or non-crossing partitions on respectively 2 n or n points. Okay, so one for the top, one for the bottom. So pi will be the object on the top, and rho will be the object on the bottom, right? And then I can build this Mandric system by putting one on top and one on the bottom. Okay, so these are Mandric systems. So these are the objects with no requirement, no condition on the number of connected components. And here we come to the main issue, that what we want to count is connected objects, so just one connected component. So we would like to relate the number of connected components of this object pi rho here to basically to these 2 mathematical objects now, non-crossing partitions on endpoints. And this is done in the following way. So again, this is about another bijection now between non-crossing partitions and a subset of permutations on endpoints. And these permutations are very well known in combinatorics and also in free probability theory. They have been put forward by Philippe Bian, and they are constructed as follows. So these are permutations, which are called geodesic permutations. I will denote the set S and C, like permutations which are non-crossing. And these are the permutations which saturate actually this triangle inequality. So sigma is my permutation. And I want that the length of sigma plus the length of sigma minus 1 gamma. So this is the inverse permutation, and gamma. Oh, I forgot to tell you what gamma is. So gamma, this is very important. So gamma is this full cycle permutation. So it's the permutation 1, 2, 3 up to n. Okay, it's the full cycle permutation. And so in general, we have this triangle inequality, which says that the length of sigma plus the length of sigma minus 1 gamma is always larger or equal than gamma, than the length of gamma, which is n minus 1. And geodesic permutations are the ones which saturate this this triangle inequality. So what is this length? This length is the minimum number of transposition which multiply to sigma. So equivalently, if you don't want to think about this, the length of a permutation sigma, it's n minus its number of cycles. Okay, so here you see that the length of this permutation gamma is n minus 1 because this gamma is just one cycle. Okay, so this establishes another bijection. So between non-crossing partitions and the subset of permutations, and this one is very useful because it allows us to express the number of connected components of a Mandric system, which is built out of pi on top and rho on the bottom. And this number of connected components is exactly the number of cycles of the permutation pi minus 1 rho. So you can think of it's kind of a distance between the permutations pi and rho. Okay. So now we have expressed all this problem about meanders and Mandric systems in terms of this geodesic permutation. So I have one on the top, one on the bottom, and the number of connected components is the number of cycles of pi minus 1. Okay, so this was first observed by Nica. And now let me introduce some notation. So M and R will just be the number of Mandric systems, so the number of pairs of non-crossing partitions which have R connected components, so such that the number of cycles of pi minus 1 rho is R. Okay, and so meanders, so objects, so Mandric systems with one connected component, so connected Mandric systems is just the thing with R equals 1, so one connected component. So these are meanders. So these are the objects that we are ultimately interested in. Okay, so now that you have a mathematical formulation of the problem, we want to have a formula or to get some kind of grasp on the cardinality of the set Mn1. Let me tell you what is known about these objects. Okay, so the sequence that we are interested in is the cardinality of meanders, so the cardinality of Mn1, and here is the reference in the online encyclopedia of integer sequences. And we have two simple bounds. So of course, meanders are Mandric systems. So this is the number of Mandric system. I have Catalan possibilities on top, Catalan possibilities on the bottom. So this is Catalan n squared. So we have this trivial upper bound, and the lower bound is given by the fact that so there's this construction which is called Krevra's complement. I don't want to talk about it right now, but we have it's also lower bounded by Catalan n. And there is no known formula for this Mn1, but maybe we can say something about the asymptotic growth of the sequence. So it has been conjectured that it behaves like constant times so it has an exponential behavior, so a to the n, that times the polynomial factor n to the minus b for some constants c, a, and b. And there are many results in this direction. So the value of the exponential growth here, so this coefficient a, which is basically the key one, it has been bounded between basically 11 and almost 13. And numerically, well, you can do computer simulations, and people have found that this coefficient should be 12 something. And there are some conjectures coming from conformal field theories and some stuff which is somehow complicated and comes from a more physics, theoretical physics, which is that this coefficient, which here b, which is supposed to be follow some universality class of CFTs, should be given by this formula, but I cannot comment more on this. I don't know how strong the evidence is for this conjecture. I cannot judge on this. And so these were basically the kind of the early days of combinatorics of meanders. And then Nica came with this idea that one should study meanders since meanders are built out of non-crossing partitions which are the central objects in free probability theory. One should use free probability theory to tackle this problem. And he and in his paper from 2016, he started this line of research. And later, with Goulden and Puder in this paper in last year, they studied a subclass of Mandric systems, which are called shallow top meanders. So what are these? These are Mandric systems with actually with one restriction on them, is that the thing on the top, so the non-crossing pairing on the top shouldn't be should have depth at most 2. You see, so the number of arches which go on top of each other should be at most 2. So here you see this is the case for the thing on the top, but you see for the thing on the bottom this is not the case because we have depth 3 over here. Okay, so this is a subclass of meanders, of Mandric systems, and in particular of meanders, and they have been able for this subclass, which is quite simpler than the class of meanders, because the structure of the thing on the top is much simpler. They have been able to count how many meanders, so how many objects like this which are connected. So here's one example which is connected, and they have found an explicit formula for this. This time using kind of combinatorial techniques. Okay, so and this kind of this, I would say, revigorated a little bit research in this direction, because one has a lot of tools in free probability, so one hopes that one can leverage these tools to tackle this problem, and they have been quite successful in this direction. Okay, good. So let me move on. So the first class of results that I would like to tell you about today. So these are quite old, like they have 5 years old now. It's about meandric systems with many connected components. So the idea is that, well, recall that so meandric systems are just pair of non-crossing partitions, and the number of connected components of such an object is given by this number of cycles of permutations. So the main question is about meanders, right? So these are the objects which have one connected component, so which are connected, and this is a hard problem. On the other side of the spectrum, we have meandric systems which have n connected components. This is the maximal number of connected components. So basically, these are just things which have which are like this, right? Which have so basically, you can have n connected components if and only if the number of cycles of permutations of size n is n. So this means that the permutations need to be equal. And then you have, of course, you have Catalan n such objects. So basically, we have a problem here which is on top, which is very hard. The problem on the bottom, which is so r equals 1 is hard, r equals n is very easy, is trivial. So basically, what we did with Moto is said, well, I mean, let's start from the easy one and work our way up. So let's look at what happens for Mandric systems on 2 endpoints, but with a large number of connected components. And by this, I mean almost maximum. So the number of connected components will be n minus r, where you should think that r, this parameter r, will be fixed, and n will be arbitrary. So basically, I want to look at Mandric system which have n minus 1 connected components, n minus 2 connected components, etc. So I want to go into this direction from very easy and see how far can we get towards the hard one. Okay. And let me tell you how we did this. So this is going to be a little bit the technical part of this talk. So let me walk you through this. So what we're going to do is we're going to study this problem with generating series. So let's build this function m of 2 parameters x, y. So y will count the number of connected components, and x will count the order of the meander, right? So basically, I encode this sequence m and r into a generating function. So this is how it looks like. So this function, I can write it as a sum over all non-crossing partitions of size n. And remember that this is the number of cycles is what matters for us. And the first step that we will take, the first equality here, is to say, well, let's package this sum into subsets such that the supremum of these 2 non-crossing partitions, so the partition which you get when you put together these partitions and you look at the smallest non-crossing objects, which is larger than both of them, so the sup of these 2 non-crossing partitions, let me call it omega. So let's package this sum into packets into subsets which have the same supremum omega. And once you do this, you realize that once you have the sum here, you can decompose the sum. You can write the sum as a product over the blocks of this non-crossing partition omega of something. And now you see that if you don't care too much about what is in here, is that you'll see a formula which looks like a sum over xn. So this is the generating function part, a sum over all non-crossing partitions omega, and then a product over the blocks of omega of some function which depends on the size of the block and this counting variable y here. Okay, and here, if you are familiar with probability theory, you will see that this looks a lot like this is the moment-cumulant formula from free probability theory. So this kind of think of these as the moments of some random variable, and these things here you can think of them as the cumulants, or the coefficient of the Fourier transform somehow of the same random variable. And this allows basically somehow the idea is that these objects here, the cumulants, should be morally easier than the moments which we started from. So then the idea is to shift now. Let's study now these objects over here, knowing that going from cumulants to moments to the original thing is a well-known procedure in free probability theory. So basically, it's like we kind of simplify the problem in one step. So now we introduce the generating function of these cumulants. So remember that the second sum I had on the last slide was again some kind of objects, kind of a Mandric system. So again, I have this pi and rho, but with the same condition on the number of connected components. But now I have this extra condition that the supremum of pi and rho should be 1. So basically, this means that I cannot have, I can have some object here, some meander, I don't know, something on the other side, and I cannot have a split between the two. So it means that I'm looking somehow at the irreducible Mandric systems in some way. And now the idea is that this function k should be a bit easier than the original function m, and nonetheless, the functions m and k are related by the by Voiculescu's moment-cumulant formula. So there is this. You see, there is this equation relating the two generating series m and k. Unfortunately, this equation is implicit, right? So imagine that you know perfectly the function k. In order to find m, you need to solve this. You need to solve this this equation basically for m. And depending on the actual expression of k, this might be easy or hard, right? Sure. And okay, so this was kind of the first reduction, and then the idea is to go one step further, to introduce another set which is even simpler than k, and maybe for this set we can get a grasp. We can get a grasp of this set. And the idea is that we can finally introduce the set I which states for irreducible, which are the set of Mandric systems, which such that not only the supremum of these two non-crossing partitions is the full partition, but also that the infimum is the zero partition. So it's the smallest element in the set. And again, I have this condition on the number of connected components. And it turns out that the relation between the function k and I, it's of the same flavor as before. It's again a moment-cumulant formula. So so you see, we added an extra condition on our non-crossing partitions, and we simplify the problem, and we have again a relation of this type between the two generating series. Okay, so I know it's been a bit fast, so let me summarize what we have done. This is the original problem that we were studying: Mandric systems with R-connected components, and then we introduced somehow some other sets of Mandric systems which have extra conditions. So about the supremum, and here the supremum and the infimum of these two partitions, and we built generating series MKI out of these sets. And it turns out that these generating series, excuse me, are related by this moment-cumulant, moment-free cumulant transform in free probability theory. And the idea is that somehow the complexity of these objects should go down. Okay. So now the idea is that since these things are related, let's try to enumerate these simpler objects I. And here is the main observation from our work, is that if you fix R, so R, remember, is the difference between n and the number of connected components. We are in the regime where we look at Mandric system with lots of connected components, so R is fixed. Then the series I. So remember that I is a series which has two counting parameters, one for n and one for R. So if you fix R, there is just a finite number of n's such that the set is non-empty. Okay, so this is the key observation. And basically we're saying that the set is empty unless n is between basically R or 2R. Okay. So here's an example. Here are these meandric systems. So R equals 1. Here are the only pairs of meandric systems. So you have to build out of these two non-crossing partitions, which you can do for R equals 1. Here is a more maybe a clearer picture for R equals 2. So for R equals 2, n can be either 3 or 4. So these are the meandric systems in I3, 2, and here are the 4 meandric systems in I4, 2. And you see these things are kind of connected. I cannot separate them. They are not, they are not separated. So I cannot split them in two. And moreover, I don't have matching things on the. So this is the supreme condition, and the infimum condition mean that I don't have matching things on top and on the bottom. So, I don't have things which are mirrored from top and bottom. And you see for R equals 2, I have only n equals 2 or 4. So this is my the coefficient of y squared in this generating series. It has a finite support in n. So the powers here are only 3 and 4. They don't go up to infinity. So the idea is this somehow. For fixed R, this generating series the coefficient of y to the R in this generating series is kind of simple. Well, I'm saying it's simple, but unfortunately, we don't have a way to get an analytic formula for this. Let me tell you what we do. So the theorem in our paper from 2 years ago is the following. Again, you fix R larger than 1, and the claim is that there exists some polynomial of degree which is at most 3R basically, such that we can express the generating function of Mandric systems on endpoints with n-R connected components. We have an explicit formula of the generating series after a change of variables. I spare you the technicalities. In terms of this polynomial P tilde R. And this polynomial P tilde R, this is computed in terms of these objects I that I presented in the previous slide. Unfortunately, as I told you, we cannot enumerate this set for fixed R, but we can use the computer to basically go through all possibilities and see what it looks like for R smaller than 6. Of course, one can go much higher, but we stopped at 6, and we can find some expressions for this polynomial P tilde. Up to 6, they become more and more complicated, and after 6, one has to do some real programming, some not amateurish programming, so to go beyond that. But in any case, for small values of R, we can enumerate explicitly these objects I and R and get these polynomials. And the result is as follows: we have a formula for the generating series for these meanders. And we also can get some precise asymptotic behavior as n goes to infinity for the number of Mandric systems with large number of components. Again, let me go back to my first slide here. This is in the regime where the problem should be easy, right? So we are close to the easy regime where, however, we would like to go up to here. So the limitation of this method is that we can only go to n-1, n-6, some finite n minus finite something, and we'd like to go all the way to R equals n. But this seems out of reach with this method. Okay. Good. Now let me now move on to these shallow top Mandric systems. Let me recall you what these were. So these were again these objects where I impose a constraint on what happens on the top. So on the top, I ask that the depth of the object on top should be at most 2. So I allow for this kind of depth 2 or 1, but I don't allow for objects of depth 3 like here. So the top is simpler than the bottom. So the structure on the bottom can be very intricate. You can have arches going on top of the other. So this is what makes the problem difficult. But on the top, things are very simple. And so this is the picture, remember that this is the picture where the object in red here is drawn as a non-crossing pairing on these two endpoints. But you see, if I were to go to the picture where I unfatten these partitions, so here here is what they look like, I get what is called an interval partition. So the blocks of this partition here are just intervals. I cannot have things which which skip objects. So this is not allowed in here. Okay. So this means that the partition pi, which is responsible for the top of the picture, is an interval partition, which and its structure is much more manageable. And now we follow basically the same idea as in our paper from 2 years ago, doing the same transformation. So going from M to some simplified or simpler object K, and then again to some even simpler object I. And since now the top is much easier, and it's these interval partitions, here we can use a Boolean transform. So this is another type of non-commutative probability, which is called Boolean probability, where non-crossing partitions are replaced by interval partitions, which are much more easier to understand. So it's just an interval partition. It's just you have to say where each interval ends and the next one begins. So you don't have things which hop. So it's much more manageable. And in this case, it turns out that we can actually compute analytically this generating series I on the left hand here, on the left hand here. So then once we know I, we can go back using the transfers to the original M. So this is the result. Now, in this case, we have an explicit formula for the generating series of shallow top meanders, and this is somehow you can think of this as generalizing the result of Goulden, Nica, and Puder by saying that, well, not only we have expression for meanders, we can have the generating series for all these objects together. So it's the same type of formula. You have a sum over M, so this is the order of the meander, and then I have a sum over all shallow top meanders. So you see, the point is that the bottom is a non-crossing partition as before, but the top partition is an interval partition. This is what the simplification will appear. And then I have a parameter which counts, kind of the number of cycles of the meandric system. And then I have a parameter A, which counts the number of blocks of the partition on top, and the parameter B, which counts the number of blocks of the partition on the bottom. So we have even more detailed information. We can do all these statistical parameters. And here is the magic. So this function M, which is the one we want, going from M to K. So this Boolean transform here is much simpler. So here we don't have an implicit equation, but we have an explicit equation. So M as a function of K is just K over 1 minus K. So this is what the Boolean transform here does. And then again, to go from K to I, we have to use this this implicit free transform. But as I said, the generating function I, we can express this generating function. We have a formula, depends on these two things, G and H. And here we have explicit formula. So H is the generating function of these numbers and of these objects, and G is the generating function of these things here. So everything, the point is that everything is explicit here, and here we can solve this equation for K. And once we have K, we can plug it in here to get M. So so here basically everything is known, because instead of having two free transforms, so having non-crossing partitions on top and on the bottom, we only have one. And we have another Boolean transform which is responsible for the thing on the top here. So of course all the credit here. So all the credit here goes to Andrew Nica and his collaborators, which notice that indeed placing this restriction on the top simplifies a lot the problem, and one can go through the combinatorics, either directly combinatorics as they did, or using some non-commutative probability techniques like these transforms over here. But the main idea here is that if the thing on top is if the structure on the top is simpler, then you can do the combinatorics basically. Okay, so with this, I would like to move on to random matrix models, unless there are questions about these like a non-commutative probability approach. Okay, let me continue then. So now let me switch completely, completely switch gears and tell you about some random matrix models for these combinatorial objects. So as in that's this idea that that if you compute moments of some classical distribution of random matrices, then the generating series that you see that you get will have some integer coefficients, and these integer coefficients will count some combinatorial objects like combinatorial maps of some genus and stuff in this spirit. So this has been a very fruitful line of research. So let me tell you about this the first random matrix model by which was historically the first one. So this meander polynomial is, again, you fix n here, so and then you sum over all meanders and you look at the number of connected components. So this is a polynomial in Y. And if Francesco was the first one to propose a random matrix model for these objects, and this is as follows. So this meander polynomial, if you evaluate it at an integer value of the parameter, so k is an integer here, then this is the asymptotic 2nth moment of a random matrix of the following type. So what you need to do is you need to take k. So remember, k is the value of the parameter in which you want to evaluate this polynomial. So you need k IID, so independent GUE random matrices. And then you have to build this tensor product. So the tensor product is very important here. So this is the one kind of the main feature of this random matrix model, that a tensor product appears. So BI tensor conjugate, the complex conjugate on the BI, and then the 2nth moment of this random matrix model gives you basically the meander polynomial in the limit of large random matrices. This is the first model which appeared. And then Fukuda, so my collaborator Motohisa Fukuda and Sniady, they observed in that this is also related to a problem in quantum information theory, which is the following one. Take a V-sharp matrix, a V-sharp random matrix. So remember that a V-sharp random matrix is just a Gaussian random matrix, so without any symmetry, times its adjoint. So this is a positive semi-definite random matrix, a very standard model of positive semi-definite random matrices. So you take such a V-sharp matrix where G, so this is the parameter. So this means that G is a matrix which is of size D squared times K. Okay. So think D very large and K fixed. So you see this V-sharp matrix now, which is built out of this G, will be a matrix of size D squared, but which will have very small rank, so rank K. And then what you do with this V-sharp matrix W is that you take its partial transposition. So this is a matrix of size D squared, and then you do nothing on the first tensor factor, and then you transpose the second part of the second tensor factor. So now doing this partial transposition, this is something that people in quantum information theory like a lot, because this is one of the most famous criteria to test for entanglement, these kind of quantum non-classical correlations. So this was basically their motivation. So and they observed that if you compute the moments of this partially transposed V-sharp matrix in this very special regime where the matrix has small fixed rank, then you get the meander polynomial. Okay. So these two things seem very different, but there is still a very common feature of these two random matrix models, which to my mind is this tensor product. So basically you need tensor products to get back these meander polynomials, and this is why what makes these meander polynomials somehow hard, because you have random matrices. You have to take tensor products of random matrices. And in our work, we suggested maybe even simpler random matrix models, and which are even closer to what people in quantum information are used to. And the idea is now to consider random completely positive maps on one side, and then to apply a tensor product of such maps to a maximal entangled state. So let me tell you how this construction goes. So again, take these Gaussian matrices I was mentioning on the previous slide. So these are matrices of size D squared times K, and each entry is a complex Gauss. Okay, so no symmetry whatsoever. And out of these matrices G and H, you can build a map, a completely positive map, which goes from MK to MD in the following way. you take your input X, so this is a K by K matrix. You conjugate it by your Gaussian matrix. Here I call it A, but A is either G or H. Now you land in MD tensor ND, and then you trace the second tensor factor ND. You do nothing on the first one, so you end up with a matrix in MD. So this is what is known as the Stein-Spring dilation theorem. So every completely positive map can be written like this. And if you want, this is a standard. This is maybe a very canonical way to build such random completely positive maps, right? You take this matrix here, which you need to conjugate with to be a Geneva matrix. So IID Gaussian matrix. Okay. So this way we have a model for these random CP maps. So the idea is to take two independent such random completely positive maps, and then apply these maps to a state omega k, which is known as the maximal entangled quantum state. So what is this maximal entangled quantum state? This is a rank one matrix, which is the rank one projection on this vector, sum over I of EI tensor EI, right? So let me write it down here. So this omega k is just this omega k, so a capital omega k, so it's a rank one state where this omega k is just sum over I of EI tensor. Okay. So this is a state which is maximal entangled. It's here, I mean the maximum entanglement means that here you have the same I. So this is what entanglement means in this framework. And the point is that if you do this, then again you get back the moments of this random matrix Z. Give you back the Meander polynomial again in the same regime. So K is fixed. You evaluate the Meander polynomial as integer K parameter. Okay, so this is actually, you see, it's the same. It's always the same feature. You have some tensor product which appears. It seems that you cannot escape the tensor product of random matrices if you want to get a matrix model for Meander's for the Meander polynomial. Now, how about these shallow top meanders that I mentioned before? So these were like kind of a subset of all the meanders which are kind of easier to consider. Well, the idea, I mean, I would spare you the details, is that there is a small technicality here, but don't worry too much about this. Basically, the idea is that you get the same construction. So forget about this Z0, doesn't matter too much. So you build this random matrix Z in the same way, but now basically you only have one copy of this random CP map, and on the other half of this maximal entangled state, so it's the same. You have this maximal entangled state here, but on the second space of this maximal entangled state, you don't act with this phi h we had before here, but you act with a fixed object, a non-random object, a fixed channel, which is this one. It's called a depolarizing channel in quantum information. Again, an object which people in QIT are very familiar with. And basically you recover the shallow top Meander polynomial in terms of this matrix, this random matrix Z. And you see, again, it's much simpler because instead of having, you know, a tensor product of two random objects, you just have one random object and then a deterministic, a very simple one. And again, this is due to the fact that, you know, the shallow top means that, you know, this psi here is responsible for the shallow top part, so it's quite easy to manage. Okay, so this is it. I mean, this is what all that I wanted to tell you about. Let me briefly remind you what the story was, what I wanted to tell you about. So I wanted to tell you about these meanders, these combinatorial objects which are meanders. So basically the picture here. A closed loop which intersects a horizontal line in two endpoints. These are very hard to enumerate, these objects. We don't, there are very few things known about this. And the natural generalization is to forget about the condition that you only have one loop and to allow for multiple loops. These are called Mandric systems. And the ultimate goal of this business is to enumerate meanders, to get some kind of, at least asymptotically, to get the growth rate of these of the number of meanders. And I have told you about two results. The first one is enumerating these objects here, which have not one, the interesting case, but many connected components. And this has been done with kind of ideas from free probability theory. And then following the intuition of Nica and collaborators, which told us that, you know, one should look at Mandric systems which have this shallow top. So the top has depth at most 2. that these objects are much easier to study. We also applied kind of the same ideas of using non-commutative probability, so free probability on the bottom if you want, and Boolean probability on the top, to get an explicit formula for the generating series of these objects, in particular for meanders. And finally, I showed you some random matrix models for these objects, which are related to quantum information theory and might be interesting for that community. Okay, so this was it. Thanks very much for the attention.
Thank you, Jan, very much. And are there any questions?
Sorry, can you hear me?
Yes, please, Arthur.
I have a question. I see page 19. Sorry, can you turn to page 19?
Page 19, sure, I can do this.
Well, in the middle, there is the BI and the tensor BI. I want to know when the D intends to infinity, will this converge in distribution, or will it be converged almost surely?
So this is a very good question. So it's not, I mean, you know, the distribution of this. So of course, the point is that no, because you know this BI tensor BI bar has, you know, so each term, if you would like, the eigenvalues of each term are, you know, products of the eigenvalues of each BI, right? So, and then if you basically what one would like to do is, you know, free probability theory tells us that we have a finite sum here of things which are independent. So maybe the idea would be to get a grasp on the eigenvalues of the sum in terms of the eigenvalues of the independent of the individual terms. So each term, of course, converges to some distribution, which is a square of the semicircular distribution. But the problem is that, you know, to apply these tools of that Voiculescu gave us, these you know, additive convolutions, additive free convolutions, and stuff like this, we need that the terms should be asymptotically free, and this is not the case. So one cannot compute the distribution of the sum, although we know the distribution of the individual terms, because although they are independent, the individual terms are not asymptotically free. So yeah, so we don't know how to go from one term to the sum.
Okay, thank you.
This is the main point, that if here we would have like a big random matrix, which was a big GUE, of course, then we could do it. But the tensor product here tells us that this matrix has some internal structure, and we don't know how to deal this. We do not know how to deal this in the limit. Yeah.
Okay. Thank you.
Thanks for the
I have a related question.
Yes, please.
Yeah, I was wondering, my understanding is that you would like to derive this MNK for K, which is in a continuum, no? Because even if you could compute it, it would not be enough really to.
Of course, yes, indeed. So, you know, morally, imagine that you can compute K going to infinity. So K going to infinity, the largest contribution here will be given by the thing with largest number of cycles. And this is not what we want. What we want is the objects which have just one cycle, which are the meanders. So morally, what we would like to have is K goes to zero, kind of a way. But, you know, unfortunately, K is the number of matrices here. So,
actually, I was wondering if this construction that Vaughan has of this planar algebra that we use together, actually, to exactly for the same kind of thing where we can, I mean, physicists could construct a generating function taken at integer values, and then by using this construction of Vaughan, we could get values of K, which was replaced by the index of subfactors, all the possible.
Yes, so yeah, I think so. Dimash Shaftenko told me about the same thing some years ago, that you know, you might get some K equals cosine square of something. but we haven't looked at all in this direction. So I don't. Yeah, I think it's a very good idea, and it's of course related to things that Von did. But yeah, I'm not competent to tell you anything about this.
And I have another question, actually.
Sure, Alice.
Please.
I remember that the Francesco approach was actually by using matrix model with a more complicated interaction. And I'm wondering if it's easy to see the relation. I mean, he was looking, I think, at matrix model with potential, which were quartic.
Oh.
I mean, it was not this kind of matrix models that he considered, I think, to get his heuristics.
Oh, no, of course. So this also appears in his paper, but I think this is not, you are correct. This is not the one that he used to get this this universal and this thing over here. This is what you mean?
Yes.
Yes. I think that there are other matrix models which lead to this one, not the one I presented. The one I presented here is kind of maybe the simplest one to show on a slide, I guess. But of course, there are many other matrix models for these for the meander polynomial. Indeed.
Thank you.
Thanks.
Can I ask you a question?
Yes, Arthur.
Yeah. Is it interesting to look at meanders across more than one line?
Oh, I do not know. There is quite a lot of literature, so I maybe I can point you to this paper by Di Francesco. The reference is here to this one. It's called Meander Folding and Arch Statistics. It has a lot of information and a lot of different approaches, including planar algebras and stuff like this. And maybe this generalization, you might find it in there, but this doesn't ring a bell for me. Surely, yeah.
So I was just thinking about multipartite entanglements.
Oh, yeah, maybe. I don't know. That might work. Yeah, this is a good idea. I don't know. Have to think about it.
Thank you.
Thanks, Arthur.
Any other questions? Okay, if not, we thank Jan again. Thank you very much for this.
Thanks a lot, and thanks for the very nice questions. Thank you.
And okay, and we have some minutes of break, and next